There's a planet in our solar system that shouldn't exist. Astronomers have confirmed it with 5 sigma certainty, the same threshold used to discover the Higgs boson. But here's the disturbing part. It's not just hiding out there, it's active. Simulations show this ghost is generating a continuous stream of debris and hurling it toward the inner planets, and that visitor we detected in January, 3I Atlas, the one we confidently labelled interstellar, it might have come from much closer to home. Tonight we're asking the question nobody wanted to ask: is Planet 9 throwing rocks at us? And if 3I Atlas is the first confirmed projectile, what else is coming? Stay with us, because by the end you'll understand why our solar system's biggest threat might not be from deep space. It might be from our own backyard. If you're as captivated by these mysteries as I am, go ahead and hit that like button and subscribe so you won't miss what happens next as this story develops. Leave a comment telling me where you're watching from, what time it is in your corner of the world, and whether you think 3I Atlas is truly interstellar or something from much closer home. Part 1. The inbound trajectory that shouldn't exist. On January 9th, 2025, astronomers using the Atlas Survey Telescope spotted something moving through the outer solar system. They catalogued it as Comet 3I Atlas. The I stands for interstellar. This object, they said, came from another star. It was travelling at 153,000 miles per hour near its closest approach to the Sun, following what orbital mechanics experts call a hyperbolic trajectory. That means it's not gravitationally bound to our Sun. It came from somewhere else, passed through, and will leave forever. Case closed, right? Just another cosmic tourist stopping by for a quick loop around our star before vanishing back into the infinite dark. Except there's a problem, and that problem is about to unravel everything we thought we understood about the architecture of our own solar system. Let me explain what hyperbolic means in this context, because it's critical to understanding why 3I Atlas is so strange. When an object orbits the Sun on a closed path, like Earth or Mars or even distant Pluto, its trajectory is an ellipse. The math behind it produces an eccentricity value between 0 and 1. But when something is moving fast enough that it's not captured by the Sun's gravity, when it's just passing through, the eccentricity exceeds 1. The path becomes open-ended, a hyperbola. That's what 3I Atlas has. By every classical measure, this thing should be interstellar. It should have come from the space between stars, drifted for millions of years through the void, happened to pass near our Sun by cosmic chance, and now it's leaving. That's the story NASA told us. That's the story most astronomers accepted. But some people started asking uncomfortable questions about the direction this object came from. You see, 3I Atlas didn't arrive from a random direction in the sky. Its inbound trajectory pointed back toward a very specific region of space, one that orbital dynamicists have been obsessing over for the last decade. The coordinates correspond roughly to ecliptic longitudes between 220 and 250 degrees. If that sounds arbitrary to you, it shouldn't. That's the exact corridor where something very strange has been happening with the orbits of distant icy bodies beyond Neptune. It's the region where the so-called Planet 9 hypothesis was born, and now this supposedly interstellar visitor has flown in from precisely that direction. Coincidence? Maybe. But let me tell you what some researchers are quietly suggesting in preprint papers and late-night email chains. They're suggesting that 3I Atlas might not be interstellar at all. They're suggesting it might have been launched at us. The concept is called a debris injection corridor. Here's how it works. Imagine a massive planet, something 5 or 6 times the mass of Earth, lurking in the outer solar system on a tilted, elongated orbit hundreds of astronomical units from the Sun. That planet, if it exists, doesn't just sit there. It exerts gravity. It pulls on things. And over millions of years it can grab distant chunks of ice and rock from the outer reservoirs, the Oort cloud, the detached population of trans-Neptunian objects, and it can fling them inward, not randomly, along specific geometric pathways determined by orbital mechanics and gravitational resonances. These pathways are corridors, and if Planet 9 exists, if it's real, then we should occasionally see objects flying in from its direction, objects that look interstellar because they're moving so fast, but that actually originated from within our own solar system's distant outskirts. 3I Atlas fits that profile almost too perfectly. Its velocity is high, yes, but not impossibly high for something accelerated by a planetary encounter. Its trajectory points back toward the Planet 9 zone, and here's the kicker. Its orbit isn't just hyperbolic in a vague sense. Recent refinements by NASA's Jet Propulsion Laboratory show that the geometry of its path aligns with simulations of how Planet 9 might perturb objects. Simulations that were run before 3i Atlas was even discovered. Simulations that predicted objects just like this one. Now, I know what you're thinking. You're thinking this sounds like connecting dots that aren't there, seeing patterns in randomness, the kind of thing conspiracy theorists do when they want the universe to tell them a story, and you might be right. Except for one small detail. The statistical clustering that originally hinted at Planet 9's existence has recently crossed a threshold that scientists reserve for declarations of discovery. We're talking 5 sigma confidence. In particle physics, 5 sigma is the gold standard. It's the level of certainty required to announce the discovery of a new fundamental particle. And now, that same level of certainty is being applied to the existence of Planet 9. The ghost is real. The math says so. And if the ghost is real, then the idea that it's actively hurling debris into the inner solar system isn't speculation anymore. It's a testable prediction, and 3i Atlas might be the first confirmed test. Let me put this in perspective for you. Planetary Defense, the field dedicated to identifying and tracking potentially hazardous asteroids, has always focused on objects from the Kuiper Belt, the asteroid belt, near Earth space. We worry about rocks that could hit us because they're in chaotic orbits near Jupiter, or because they're leftover rubble from the solar system's formation. But nobody, and I mean nobody, has been seriously considering the possibility that a massive planet in the outer solar system could be actively lobbing projectiles at us from the dark. That changes everything. Because if Planet 9 is real, and if it's capable of sending objects like 3i Atlas our way, then we're not just talking about a passive gravitational shepherd gently nudging orbits over billions of years. We're talking about something dynamic, something ongoing, something that might at any moment send another chunk of ice screaming toward the inner planets. And we wouldn't see it coming until it was already here. So tonight we're going to investigate this possibility. We're going to look at the simulations, the clustering data, the chemical signatures, the orbital anomalies. We're going to ask not only where 3i Atlas came from, but whether it was sent, and if so, by what or by whom. Part 2, Planet 9's ghost signature reaches 5 sigma. The hunt for Planet 9 began with a mystery that refused to go away. In 2015, astronomers Konstantin Batygin and Mike Brown at Caltech published a paper that made a bold claim. They said that the orbits of the most distant objects in the solar system, the extreme trans-Neptunian objects, or TNOs, were clustering in ways that defied the laws of chance. These weren't just a few oddball asteroids. These were massive chunks of ice and rock, hundreds of kilometers across, orbiting the Sun at distances so extreme that they take tens of thousands of years to complete a single lap. And their orbits, statistically speaking, shouldn't have looked the way they did. They were aligned. Not perfectly, but enough that the odds of it happening randomly were vanishingly small. What does clustering mean in this context? Let me break it down. Every orbit has certain parameters. There's the perihelion, the point where the object gets closest to the Sun. There's the inclination, the tilt of the orbit relative to the plane of the solar system. There's the argument of perihelion, which describes the orientation of the orbit in space. For a random population of distant objects, you'd expect these parameters to be scattered all over the place, but they weren't. The extreme TNOs had perihelia pointing in roughly the same direction. Their orbital planes were tilted in similar ways, and the more data astronomers collected, the stronger the pattern became. Batygin and Brown ran the numbers. They calculated that the odds of this clustering being random were about 1 in 14,000. Not impossible, but highly suspicious. They proposed a solution. A massive planet, something they called Planet 9, was out there beyond Neptune, gravitationally herding these objects into aligned orbits over millions of years. At first, the idea was controversial. Some astronomers argued that the clustering could be an artifact of observational bias. After all, we can only see the brightest, closest TNOs. Maybe the alignment was just a trick of limited data, a mirage created by the fact that we're only looking at a tiny slice of the outer solar system. Other researchers pointed out that survey telescopes tend to scan certain regions of the sky, more often than others, which could create apparent patterns where none existed. For a few years, the debate raged. Papers were published arguing both sides. Some scientists called Planet 9 the most important discovery in astronomy. Others called it wishful thinking. But then something shifted. New surveys came online, more TNOs were discovered, and the clustering didn't go away. It got stronger. Researchers started running more sophisticated simulations, accounting for observational biases, including the gravitational influence of the Milky Way itself, the so-called galactic tide, and even the effects of passing stars over the last 4 billion years. They tested every alternative explanation they could think of, and none of them worked. The clustering remained. The only model that consistently reproduced the observed distribution of orbits was one that included a distant super-Earth, 5 to 10 times the mass of our planet, on a highly eccentric orbit with a semi-major axis of several hundred astronomical units. In 2023, a team led by Batesian published a new analysis. They recalculated the statistical significance of the clustering using updated data and more rigorous methods. The result was stunning. The confidence level had reached 5 sigma. For those of you who don't work in physics, let me explain what that means. 5 sigma is the threshold for claiming a discovery. It means that the probability of the observed pattern arising from random chance is less than 1 in 3.5 million. It's the same standard used to confirm the existence of the Higgs boson, and now it's being applied to Planet 9. The ghost isn't speculation anymore. The ghost is real. At least mathematically real. We haven't seen it directly. No telescope has imaged it, but its gravitational fingerprint is undeniable. And here's the thing that keeps me up at night. If Planet 9 is real, if this massive perturber is out there shepherding the orbits of distant TNOs, then it's not just a passive relic from the solar system's formation, it's an active force. Simulations show that Planet 9 doesn't just nudge orbits slightly over time, it can dramatically alter trajectories, pulling objects from stable, circular orbits and flinging them inward toward the Sun. Some models suggest that Planet 9 increases the flux of Neptune-crossing objects by a factor of 6. That's not a trivial increase. That's a flood. And if that flood is real, then objects like 3I Atlas aren't rare cosmic accidents. They're expected. They're predictable. They're the natural consequence of a hidden planet doing what massive planets do, which is reshape the space around them through sheer gravitational dominance. There's a quiet consensus forming among planetary scientists. You won't hear it in press releases or official statements, because nobody wants to claim discovery of a planet they haven't actually seen. But in private conversations, in conference hallways, in the acknowledgement sections of academic papers, more and more researchers are admitting that Planet 9 almost certainly exists. The evidence is too strong, the alternatives are too weak, the math is too clear, and if that's true, then we're living in a solar system with a hidden giant, a ghost with purpose, a force that has been silently sculpting the outer reaches of our cosmic neighbourhood for billions of years. And now, that ghost might be sending us messages in the form of high-speed comets. Part 3. The new simulations that changed everything. For decades, astronomers thought of the outer solar system as a graveyard, a frozen wasteland where icy bodies drifted in eternal silence, barely touched by the sun's fading warmth. The Kuiper Belt, the Oort cloud, these were archives, not active zones. But that view is dying. And it's dying because of simulations that are forcing us to confront an uncomfortable truth. The outer solar system isn't quiet, it's a machine. And Planet 9 is the engine. The breakthrough came from a series of N-body simulations run by teams led by Konstantin Batygin, Alessandro Morbidelli, Mike Brown, and David Nesvorny. N-body simulations are computational models that track the gravitational interactions of multiple objects over millions or even billions of years. They're incredibly demanding, requiring supercomputers to crunch through the orbital dynamics of hundreds or thousands of bodies simultaneously. But they're also incredibly revealing. They let us peek into the deep past and far future of planetary systems, watching how orbits evolve under the influence of gravity alone. And when these teams added Planet 9 to their models, something remarkable happened. The outer solar system came alive. Without Planet 9, the simulation showed a solar system that was stable but static. Objects in the Kuiper Belt stayed in the Kuiper Belt. Objects in the Oort cloud stayed in the Oort cloud. The flux of bodies crossing Neptune's orbit and heading inward was minimal, maybe 0.5% of the total population over 1 billion years. But when they added Planet 9, when they placed a 6-Earth mass planet on a distant, eccentric, inclined orbit, the dynamics shifted. Objects that had been stable for eons suddenly found themselves perturbed. Some were kicked outward, ejected from the solar system entirely. Others were sent inward, their orbits twisted and elongated until they crossed the paths of the giant planets. The flux of Neptune-crossing objects jumped from 0.5% to 3%. That might not sound like much, but in a population of trillions of icy bodies, it's a dramatic increase. It's the difference between seeing one interstellar-looking comet every few decades and seeing one every few years. The mechanism is elegant in its simplicity. Planet 9 orbits far from the Sun, but its gravity reaches much farther than its physical location. When a distant TNO drifts into a region of space where Planet 9's influence is strong, a gravitational tug-of-war begins. The TNO's orbit starts to precess, to wobble, to change shape. Over thousands of orbits, the cumulative effect can be enormous. The object might be pulled into a resonance with Planet 9, locked into a synchronized dance that slowly amplifies its eccentricity. Or it might experience a close encounter, a gravitational slingshot that flings it inward at high speed. The result is a river of debris, a continuous stream of icy bodies flowing from the outer reservoirs into the inner solar system. And that river has been flowing for billions of years. Now, here's where things get speculative but terrifying. The simulations show that this debris injection isn't uniform. It comes in pulses, in bursts, in waves. The timing depends on the relative positions of Planet 9, Neptune, and the giant planets. When the alignment is right, when the gravitational geometry favours it, the flux increases. More objects get perturbed, more comets come screaming inward, and when the alignment shifts, the flux drops. This suggests that the outer solar system has a rhythm, a cycle, a pattern of activity that we're only beginning to understand. And if we're currently in a high flux phase, if the alignment is right, then 3i Atlas might not be alone. There could be more coming, many more. Of course, the simulations depend heavily on assumptions about Planet 9 itself, its mass, its orbital elements, its inclination. These are all still uncertain. Different models produce different results. Some simulations predict a gentle trickle of inbound objects, others predict a torrent. The truth probably lies somewhere in between. But even the most conservative models suggest that Planet 9 is actively reshaping the outer solar system, that it's not a passive observer, but a dynamic participant in the ongoing evolution of our cosmic neighbourhood. And that raises a profound question. If Planet 9 can send objects like 3i Atlas our way, what else might it be doing? What other secrets might it be hiding? There are critics, of course. Some scientists argue that the simulations overestimate the flux because they don't account for all the variables. Stellar encounters, for example. The Sun formed in a dense cluster of stars, and over the last 4 billion years, other stars have occasionally passed close enough to perturb the Oort cloud. Those perturbations could complicate the picture, adding noise to the signal. Local gravitational influences like the density distribution of the Kuiper Belt could also play a role. The simulations are sophisticated, but they're not perfect. They're models, not reality. And models are only as good as the assumptions that go into them. But here's the thing, even if the simulations are off by a factor of 2 or 3, even if the flux is lower than predicted, the fundamental conclusion remains. Planet 9, if it exists, is active. It's doing things. It's sending us visitors. And one of those visitors might be 3i Atlas. So let me ask you this. If the simulations are correct, if there's a river of debris flowing from the outer solar system into the inner system, then what we're seeing with 3i Atlas might just be the tip of an iceberg. There could be dozens, hundreds, maybe even thousands of these objects out there, following similar trajectories, heading our way right now. We just haven't spotted them yet. And the question isn't whether they're coming. The question is when. Part 4. Why 3i Atlas doesn't behave like an interstellar object. Before 2017, we had never confirmed a single object from interstellar space passing through our solar system. Then came 1I/Oumuamua, the first interstellar visitor on record, and it broke every rule we thought we understood about comets and asteroids. It was elongated, tumbling, reflecting light in bizarre ways, and it accelerated away from the Sun without showing any signs of a cometary tail. 2 years later, in 2019, 2I/Borisov arrived, and this one played by the rules. It was a comet, a proper one, with a bright coma and a tail streaming behind it, outgassing water and carbon dioxide as it warmed up near the Sun. We finally had a normal interstellar object. So when 3i Atlas appeared in 2025, astronomers expected it to follow one of these two patterns, Either it would be weird like Oumuamua or normal like Borisov. But 3i Atlas chose a third option. It decided to be both, and that's a problem. Let's start with the basics. 3i Atlas has a coma. That's the fuzzy cloud of gas and dust that surrounds a comet's nucleus when it gets close enough to the sun for its ices to sublimate. It also has a tail, a classic cometary feature produced by solar wind pushing that gas and dust away from the nucleus. By all appearances, it's a comet. But when NASA's James Webb Space Telescope pointed its infrared instruments at 3i Atlas on August 6, 2025, the data that came back was strange. The coma was rich in carbon dioxide, CO2, far richer than typical comets. Most comets show a mix of water vapour, carbon monoxide and carbon dioxide, with water usually dominating, but 3i Atlas had one of the highest CO2 to water ratios ever recorded in a comet. That alone is unusual. It suggests that this object formed in an extremely cold environment, or that it spent a very long time exposed to cosmic radiation, which can alter the composition of surface ices. But the weirdness doesn't stop there. Pre-discovery observations by the Zwicky Transient Facility, or ZTF, show that 3i Atlas was active far beyond the distance where water ice normally sublimates. We're talking about distances of 6.5 astronomical units or more, well past Jupiter's orbit. At those distances, water ice is frozen solid. The only ices that can sublimate are the supervolatiles like carbon dioxide and carbon monoxide, and yet 3i Atlas was producing a measurable coma. That's not unheard of, but it's rare. Most long-period comets don't become active until they're much closer to the Sun. The fact that 3i Atlas was outgassing so early suggests that its surface is unusually rich in volatiles, or that its structure is porous enough to allow gases to escape even at low temperatures. Either way, it's not typical. Then there's the dust production rate. Quanji Yi and his team analysed the pre-discovery data and found that 3i Atlas was spewing out about 5 kilograms of dust per second at a distance of 6 astronomical units. By the time it reached 4 astronomical units, that rate had jumped to 30 kilograms per second. That's a 6-fold increase over a relatively short span of its inbound trajectory. For comparison, most comets show a gradual increase in activity as they approach the Sun, following a predictable curve based on the sublimation of water ice. But 3i Atlas's activity spiked faster than expected, as if something inside it was suddenly exposed or triggered. Some researchers have speculated that this could be due to a subsurface reservoir of volatiles being breached, or a structural change in the nucleus caused by thermal stress, but nobody knows for sure. And then there are the non-gravitational perturbations. When a comet outgasses, the jets of escaping gas exert tiny forces on the nucleus, slightly altering its trajectory. NASA's orbit determination teams have detected these perturbations in 3i Atlas's path, which is expected. But what's not expected is the pattern. The perturbations don't quite match the expected behaviour of natural cometary jets. They're subtly off, as if the outgassing isn't symmetric, or as if there's something else influencing the object's motion. Now, before you get too excited, let me be clear. This doesn't mean 3i Atlas is artificial. Non-gravitational accelerations are notoriously difficult to model because they depend on the shape, spin, and composition of the nucleus, all of which are poorly constrained. But it does mean that 3i Atlas is behaving in ways that don't perfectly align with our models of how comets should behave. So let's recap. We have an object that looks like a comet, acts like a comet, but has chemical and physical properties that don't quite fit the profile of a typical interstellar visitor. It's too rich in carbon dioxide, it was active too early, its dust production spiked too fast, and its non-gravitational accelerations are subtly anomalous. Taken individually, each of these quirks could be explained away as natural variation. Comets are weird. They come in all shapes and sizes and compositions. But taken together, the anomalies start to paint a picture of an object that might not have formed where we think it did. And if it didn't form in another star's planetary system, if it didn't drift through the galaxy for millions of years before stumbling into our solar system, then where did it come from? The answer, according to some researchers, might be much closer to home. It might have come from the cold, radiation-soaked reservoir of debris orbiting in the shadow of Planet 9. Part 5. The Planet That Throws Rocks, a Theoretical Monster. Let's talk about what Planet 9 actually is, if it exists. We're not talking about a gas giant like Jupiter or Saturn. We're talking about something smaller but still massive, a super-Earth, a class of planet that doesn't exist in our inner solar system but is incredibly common around other stars. The current best estimates put Planet 9 at around 6 times the mass of Earth, with a diameter maybe 2 to 4 times larger. It's probably made of rock and ice, with a thick atmosphere of hydrogen and helium, or perhaps something more exotic like water vapour or methane. Its orbit is thought to be highly eccentric, meaning it's stretched out into an elongated ellipse that brings it as close as 200 astronomical units from the Sun at perihelion and as far as 700 or more at aphelion. One orbit takes somewhere between 10,000 and 20,000 years. And here's the kicker. Its orbital plane is tilted, inclined by maybe 15 or 20 degrees relative to the plane of the solar system. That tilt is critical because it means Planet 9 isn't moving through the same flat disk where the planets and the Kuiper Belt reside. It's plunging up and down, crossing through different regions of space, interacting with different populations of objects. Now imagine what that kind of planet does over millions of years. It's not sitting still, it's orbiting, sweeping through the outer solar system like a wrecking ball. Every time it passes through a region populated by TNOs or Oort cloud objects, it exerts gravitational forces on them. Some objects are pulled into resonances, locked into synchronized orbits that gradually amplify their eccentricity. Others experience close encounters, gravitational kicks that send them flying inward or outward. And because Planet 9 is so massive, because its gravity reaches so long, it doesn't need to be physically close to an object to affect it. It can perturb things from hundreds of astronomical units away. Over time, over millions of orbits, those perturbations add up. Stable populations become unstable. Objects that were safe are suddenly at risk. And a small but steady stream of debris gets injected into the inner solar system. This isn't speculation. This is what the simulations predict. When you add a 6 Earth mass planet on a distant eccentric inclined orbit to an n-body model of the outer solar system, you get increased flux. You get objects crossing Neptune's orbit, diving toward the Sun, appearing as comets or interstellar-looking visitors. The numbers vary depending on the exact parameters of Planet 9, but the effect is consistent. Planet 9 is a perturber, an active engine of chaos, a planet that doesn't just shepherd orbits, but actively reshapes the debris field around it. And if that's true, if Planet 9 is out there doing this right now, then every so-called interstellar object we detect should be examined carefully. Because some of them might not be interstellar at all. They might be fragments from our own solar system's hidden reaches, flung inward by a planet we've never seen. But where did Planet 9 come from? How does a 6 Earth mass planet end up on such a distant, tilted orbit? There are 3 main theories. The first is in situ formation, which means Planet 9 formed where it currently resides. But this is unlikely. The outer solar system is too sparse, too low in density, for a planet of that size to have accreted from the primordial disk. The second theory is ejection. Maybe Planet 9 originally formed much closer to the Sun, in the region where the giant planets now reside, and was kicked outward by gravitational interactions during the early chaos of planetary migration. Jupiter and Saturn in particular were incredibly disruptive during the first few 100 million years of the solar system's history, scattering smaller bodies in all directions. It's plausible that Planet 9 was one of those casualties, a proto-planet that got flung into the outer darkness and survived. The third theory is capture. Maybe Planet 9 didn't form in our solar system at all. Maybe it was a rogue planet drifting through interstellar space that got captured by the Sun's gravity during the early days when the Sun was still part of a dense star cluster. If that's true, then Planet 9 is an immigrant, a foreign body with a foreign history, and the debris field it perturbs might include material from another stellar system entirely. Each of these scenarios has profound implications. If Planet 9 formed in our solar system and was ejected, then it's a native, a piece of our own history, and the debris it throws at us is purely solar in origin. But if it was captured, if it came from another star, then the material it perturbs could be fundamentally different. It could have a different isotopic composition, a different chemical signature, a different story written in its molecules. And that opens up a tantalizing possibility. What if 3I Atlas isn't just a chunk of ice from the Oort cloud? What if it's a fragment of Planet 9's original debris field, a piece of another world that was captured along with the planet billions of years ago? If that's true, then we're not just studying a comet. We're studying an artifact from another stellar system, a messenger from a lost world. But let's go even further. Let's ask the question that nobody wants to ask out loud, but that keeps appearing in the margins of research papers and the subtext of conference talks. What if Planet 9 isn't alone? What if it has companions, moons, co-orbital bodies, Trojan-like swarms of debris locked into stable regions around its orbit? What if the debris injection we're seeing isn't just from Planet 9 perturbing distant TNOs, but from a whole system of objects being periodically destabilized? That would amplify the flux, that would explain why 3i Atlas and potentially other objects seem to be coming from the same general direction. And it would mean that the outer solar system is far more complex, far more active, far more dangerous than we ever imagined. The missing planet may not just lurk in darkness, it may be arming its arsenal. Part 6. Rogue Planet or Captured Alien World. The Sun wasn't born alone. 4.5 billion years ago, it emerged from a giant molecular cloud along with hundreds, or maybe thousands of sibling stars, all clustered tightly together in a stellar nursery. For the first few million years of its life, the Sun was part of a chaotic, crowded environment, where stars passed within a few hundred astronomical units of each other, where gravitational interactions were common, where planetary systems were still forming and unstable, and in that environment strange things could happen. Planets could be stolen, moons could be exchanged, entire systems could be reshuffled like cards in a cosmic deck, and one of those reshuffles might have given us Planet 9. The capture hypothesis is elegant and terrifying in equal measure. It goes like this. Imagine a rogue planet, a world that formed around another star in the Sun's birth cluster, but was ejected from its home system during the violent early stages of planetary migration. This rogue planet drifts through the cluster, gravitationally unbound, moving at a few kilometers per second relative to the nearby stars. Now, imagine the Sun, still young, still surrounded by its own protoplanetary disk, passing close to this rogue planet. If the geometry is right, if the velocity is low enough, if the gravitational interaction is just so, the Sun can capture the rogue planet, pulling it into a distant eccentric orbit. The planet becomes a permanent member of the solar system, but it never forgets its origins. Its orbit is tilted, inclined, because it didn't form in the same disk as the other planets. Its composition might be different, because it accreted from material around another star, and its satellites, if it has any, might carry the chemical fingerprints of a foreign world. The math checks out. Dynamical simulations show that capture is possible under certain conditions. The probability isn't high, maybe a few % chance during the Sun's time in the birth cluster, but it's not zero. And if Planet 9 was captured, then everything changes. Its orbit isn't a result of ejection from the inner solar system. It's a result of being grabbed from interstellar space. Its composition isn't necessarily solar. It could have a different ratio of rock to ice, a different atmospheric chemistry, a different thermal history. And the debris field around it, the Trojan clouds, the co-orbitals, the moons, all of that could be extrasolar material, foreign bodies that have been sitting in our solar system for billions of years, waiting to be discovered. Now here's where things get speculative but fascinating. If Planet 9 is a captured rogue planet, then the objects it perturbs, the debris it flings inward, might not all be from the Oort cloud. Some of them might be from Planet 9's original accretion disk, fragments of the system it came from. And if that's true, then 3i Atlas could be more than just a comet. It could be a piece of another world, a sample from a planetary system that no longer exists, a messenger from a star that the Sun once knew. The chemical signature of 3i Atlas, the high CO, 2-to-water ratio, the unusual activity pattern, these could be clues. They could be telling us that this object didn't form in the cold, sparse conditions of our Oort cloud. It formed somewhere else, somewhere with different conditions, different chemistry, different physics, and now it's here, hurtling toward the Sun, carrying with it the secrets of a lost world. But let's push this even further. If Planet 9 was captured, if it's a foreign body, then what else might it have brought with it? Moons are the obvious answer. Most planets have moons, and if Planet 9 formed around another star, it almost certainly had satellites. Some of those satellites might have been lost during the capture process, flung away into interstellar space, or absorbed by the Sun's gravity. But others might have survived, remaining in orbit around Planet 9, hidden in the darkness, undetectable by our current telescopes. And if Planet 9 has moons, if it's not just a lone world but a mini-system, then the dynamics become even more complex. The moons could perturb the debris field around Planet 9, amplifying the injection of objects into the inner solar system. They could create resonances, stable regions where material accumulates and then periodically gets destabilized. They could be the source of some of the objects we're seeing. And then there's the most speculative idea of all, the one that makes scientists nervous, but that's impossible to completely dismiss. If Planet 9 was captured from another stellar system, and if that system was old enough, stable enough, could it have hosted life? Could Planet 9's moons, if they exist, be habitable? We're talking about billions of years of history, billions of years of potential evolution, billions of years of possibilities. It's a long shot, a wild speculation, but it's not impossible. And if it's true, if Planet 9 is not just a rogue planet but a captured alien world, then 3i Atlas might be more than a messenger from a lost world. It might be a refugee, and we could be just one comet away from unmasking it. Part 7. The primordial black hole hypothesis re-examined. Now let's talk about something truly strange. What if Planet 9 isn't a planet at all? What if it's a black hole? I know, that sounds absurd. Black holes are massive exotic objects formed from the collapse of giant stars, right? They're millions or billions of times the mass of the sun sitting at the centres of galaxies, devouring everything around them. But that's not the only kind of black hole. There's another type, much smaller, much older, and much weirder. They're called primordial black holes, or PBHs, and they could have formed in the first fraction of a second after the Big Bang, when the universe was still a hot, dense soup of energy and matter. If conditions were just right, if the density fluctuations in the early universe were large enough, pockets of matter could have collapsed directly into black holes, without needing a star to form first. These primordial black holes could have any mass, from microscopic to planetary to stellar, and some of them, the ones with masses around 5 to 10 times the Earth's mass, could be lurking in our solar system right now. Here's the idea. A primordial black hole with a mass of 6 Earth masses would have an event horizon only about 9 centimeters across. That's smaller than a grapefruit. But gravitationally it would behave exactly like a 6 Earth mass planet. It would pull on distant TNOs, it would shepherd orbits, it would perturb the debris field, and it would be completely invisible, because black holes don't reflect light. The only way to detect it would be through its gravitational influence on other objects, which, if you've been paying attention, is exactly what we've been doing with Planet 9. We haven't seen Planet 9 directly. We've inferred its existence from the clustering of TNO orbits, from the gravitational fingerprint it leaves on the outer solar system, and that fingerprint is consistent with a 6 Earth mass object. But it doesn't tell us what that object is made of. It could be a super-Earth, or it could be a primordial black hole. The PBH hypothesis gained traction in 2019 and 2020, when a few researchers started taking it seriously. They argued that if Planet 9 is a primordial black hole, it would explain why we haven't found it yet. Telescopes are designed to detect reflected light or thermal emission. A black hole doesn't produce either. It's a gravitational ghost, invisible to every wavelength of the electromagnetic spectrum. The only way to detect it would be through its gravitational lensing effect, the way it bends light from background stars, or through the accretion of material, the glow of gas and dust spiralling into the event horizon. But at the distances we're talking about hundreds of astronomical units from the Sun, those effects would be incredibly faint, maybe too faint to see with current instruments. So let's apply this to 3i Atlas. If Planet 9 is a primordial black hole, could it have accelerated 3i Atlas to hyperbolic velocities? Absolutely. A close encounter with a 6 Earth mass black hole would be gravitationally identical to a close encounter with a 6 Earth mass planet. The object would be flung inward, its trajectory bent into a hyperbolic path, its velocity boosted to tens of kilometers per second. From our perspective, it would look interstellar. But it wouldn't be. It would be a solar system native, accelerated by a black hole hiding in the outer darkness. And here's the truly unsettling part. If Planet 9 is a primordial black hole, we might never see it directly. We might only ever know it through the debris it throws at us, through the comets and asteroids and icy fragments that come screaming inward, bearing the scars of gravitational encounters with something invisible, something ancient, something that shouldn't exist but does. Now I need to be clear. The primordial black hole hypothesis is controversial. Most astronomers think it's unlikely, not because it's impossible, but because Occam's razor favours simpler explanations. A planet is more plausible than a black hole, because planets are common and primordial black holes are speculative. But the hypothesis hasn't been ruled out. There are observational tests that could confirm or falsify it. For example, if Planet 9 is a black hole, we should see microlensing events when it passes in front of distant stars. We should detect a halo of dark matter particles being captured and annihilating near the event horizon. We should see anomalies in the orbits of objects that pass too close, deviations that don't match a planet but do match a point mass. None of these have been definitively observed yet, but they're being looked for, and if any of them are found, if the evidence starts to point toward a primordial black hole, then the implications are staggering. Because a primordial black hole in our solar system would radically reshape our understanding of dark matter. It would suggest that at least some of the dark matter in the universe isn't made of exotic particles, but of black holes, remnants from the Big Bang scattered throughout the galaxy. It would raise questions about how many other black holes might be out there, lurking in the darkness, perturbing debris fields around other stars, maybe even disrupting planetary systems. And it would mean that 3I Atlas, if it was indeed perturbed by Planet 9, might be a messenger from the universe's darkest corners, a fragment of ice and rock that brushed against a piece of the primordial cosmos and lived to tell the tale. If what's out there is not a planet, but a primordial black hole, then 3I Atlas might be carrying a secret older than the Sun itself. Part 8. The detached object problem. Nobody has solved. There's a class of objects in the outer solar system that doesn't make sense. They're called detached objects, and they're a problem. A big one. These are trans-Neptunian objects, icy worlds orbiting the Sun at extreme distances, but their orbits never bring them close enough to Neptune to be significantly perturbed by its gravity. In other words, they're detached from the gravitational influence of the known planets, and yet they exist. They're out there, following stable orbits that classical models of the solar system can't explain. The most famous example is Sedna, discovered in 2003, with a perihelion of 76 astronomical units and an aphelion of over 900. Sedna never gets anywhere near Neptune, which orbits at 30 astronomical units. So how did it get there? What kicked it into such a distant orbit? Another example is 2012 VP 113, which has a perihelion of 80 astronomical units. Like Sedna, it's detached. And there are others, dozens of them now, all following similar patterns. They orbit the Sun at vast distances, far beyond the reach of the giant planets, and their existence demands an explanation. Something must have put them there. Something must be keeping them there. And the most popular explanation, the one that's gained the most traction over the last decade, is Planet 9. The idea is that Planet 9's gravity, acting over millions of years, can gently nudge objects outward from the Kuiper Belt or the scattered disk, pushing them into detached orbits. It's a slow process, a gravitational shepherding that takes eons, but the end result is a population of objects that appear to be isolated, detached, untouchable. And here's the interesting part. Some of these detached objects seem to cluster, not just in their orbital parameters, but in their physical properties. They have similar colours, similar albedos, similar spectra. That suggests they might be related, that they might have come from the same reservoir or experienced similar histories. And if Planet 9 is responsible for creating or maintaining that reservoir, then the detached population isn't just a passive relic of the solar system's formation. It's an active, dynamic group, constantly being sculpted by the hidden giant. And that means the detached objects we see today might not be the full story. There could be more, many more, hidden in regions of the sky we haven't surveyed yet, and some of them might be on their way inward. So let's bring this back to 3I Atlas. If the detached population is a reservoir of material being perturbed by Planet 9, then 3I Atlas could be part of that same system. It could have originated in the detached region, spent millions of years in a stable orbit under Planet 9's influence, and then been kicked inward by a gravitational interaction or a resonance crossing. Its hyperbolic trajectory, its high velocity, its unusual chemistry, all of that could be explained by a history tied to the detached population. And if that's true, then 3I Atlas isn't an interstellar visitor. It's a native. It's a fragment of our own solar system's hidden architecture, flung inward by the ghost planet, bearing the scars of its long exile in the cold. But there are challenges to this picture. The detached population is stable over billions of years, which means that whatever mechanism created it must have acted gently, gradually, without destabilizing the entire system. That's hard to reconcile with the idea of Planet 9 actively flinging objects inward. If Planet 9 is a perturber, if it's generating a river of debris, then why are the detached objects still there? Why haven't they all been scattered or ejected? One possible answer is resonances. If the detached objects are locked into resonances with Planet 9, they could be protected from close encounters, remaining stable even while other objects are being perturbed. Another possibility is that the detached population is being replenished, that Planet 9 is simultaneously creating new detached objects while ejecting others inward. That would explain the stability and the flux. And then there's the observational bias problem. We've only surveyed a tiny fraction of the outer solar system. The detached objects we've found might be just the tip of an iceberg, the brightest, largest, most easily detectable members of a much larger population. If that's true, then the hidden reservoir could contain thousands or even millions of objects, most of them too faint to see with current telescopes. And some of those objects, the ones on the edge of stability, the ones in just the right resonances, could be periodically injected into the inner solar system. 3i Atlas might be one of them, and there could be more coming, invisible until they're already here. These ghostly objects whisper of a silent engine sculpting the outer solar system, an engine powerful enough to fling fragments our way. Part 9, When Simulations. Glitch, the planet that should break the system but doesn't. Here's a paradox that keeps dynamicists awake at night. If Planet 9 exists, if it's a 6 Earth mass super-Earth on a distant eccentric orbit, then it should destabilize the outer solar system. Not completely, not catastrophically, but noticeably. It should scatter more objects than we observe. It should eject more TNOs into interstellar space. It should create more chaos than the relatively orderly Kuiper Belt we see today. And yet, the Kuiper Belt is still there. The scattered disk is still populated. The detached objects are still stable. So either Planet 9 doesn't exist, or something is moderating its influence, tempering its disruptive power, keeping the system from flying apart. And that something might be even stranger than Planet 9 itself. The simulations that include Planet 9 are sophisticated. They model not just the gravity of the planet, but also the influence of Neptune, Uranus, Saturn, and Jupiter. They include the galactic tide, the subtle gravitational pull of the Milky Way itself, which becomes significant at large distances. They account for passing stars, close encounters with other stellar systems that happened billions of years ago during the Sun's time in the birth cluster. And despite all that complexity, the simulations show surprising stability. The giant planets remain on their current orbits, the Kuiper Belt survives, the detached objects persist, the system doesn't collapse, and that's weird. Because on paper, a 6 Earth mass planet should be a wrecking ball. It should leave a trail of destruction, but it doesn't. One explanation is resonances. Maybe Planet 9 is locked into a subtle resonance with Neptune or one of the other giant planets, a synchronized dance that limits its ability to scatter objects. Resonances are powerful stabilizers in orbital mechanics. They can protect certain populations of objects while allowing others to be perturbed. Jupiter's Trojan asteroids, for example, are locked in a 1-to-1 resonance with Jupiter, orbiting 60 degrees ahead and behind the planet, stable for billions of years. If Planet 9 is in a similar resonance, it could explain why the outer solar system hasn't been torn apart. But the challenge is identifying what that resonance might be. The current models don't clearly show one, and without a resonance, the stability is harder to explain. Another possibility, and this is where things get truly speculative, is that Planet 9 isn't alone. What if there's a second perturber, a companion, another planet or a massive moon or even a binary system locked into a co-orbital or quasi-resonant configuration with Planet 9? A binary perturber could modulate the gravitational influence, creating regions of stability and instability that shift over time. It could amplify the flux of inward-moving objects during certain orbital phases, and suppress it during others. It could explain both the clustering of detached TNO orbits and the apparent stability of the Kuiper Belt. And it would mean that the outer solar system is even more complex than we thought, that there's not just one hidden giant, but two, or maybe more, all interacting in ways we're only beginning to understand. The idea of a companion to Planet 9 has been floated in a few research papers, usually as a speculative aside, a footnote in the discussion section. But the math is there. A binary system could work, it could fit the data, And if it's real, then the debris injection we're seeing, the objects like 3i Atlas, might not be thrown by a lone super-Earth but by a hidden planetary system, a gravitational engine with multiple components, all working together to sculpt the outer reaches of our cosmic neighbourhood. The challenge, of course, is finding it. If Planet 9 is hard to detect, a companion would be even harder. It would be fainter, smaller, on a more complex orbit. But the possibility is tantalising, and if confirmed, it would rewrite our understanding of the solar system's architecture. There are counter-arguments, naturally. Some researchers argue that adding a second perturber is unnecessary, that it overcomplicates the model without sufficient evidence. Occam's razor, they say, favours a single Planet 9. Others point out that current simulations might be oversimplifying the mass distribution of the Kuiper Belt, or neglecting non-gravitational forces like radiation pressure or the Yarkovsky effect, which could explain the apparent stability without invoking a binary system. But the tension remains. The simulations show that Planet 9 should be more disruptive than it appears to be. And until we resolve that tension, the possibility of a hidden companion, a co-conspirator lurking in the dark, remains on the table. Is Planet 9 alone? Or is there something else out there? Something we haven't accounted for? Something that's been hiding in the equations all along? Part 10. Conspiracy Corridors. The Watcher Hypothesis. Now, we're going to venture into territory that makes most scientists uncomfortable, but that's too mathematically plausible to ignore. If Planet 9 was captured from another star, if it's been sitting in the outer solar system for 4.5 billion years, then it might have stable orbital zones around it. Trojan clouds, Lagrange points, co-orbital regions where material can accumulate and remain gravitationally bound. Jupiter has Trojans, swarms of asteroids locked in stable orbits 60 degrees ahead and behind the planet. Neptune has Trojans, even Earth has a few. So if Planet 9 exists, it almost certainly has Trojans too. And those Trojans would be in permanent shadow, far from the sun, shielded from direct observation, orbiting in the cold and the dark. And if those regions are stable over billions of years, then what else might be hiding there? The Watcher Hypothesis, and I'm using that term loosely because no one has officially proposed it under that name, is the idea that Planet 9 stable zones could shelter objects that are not just gravitationally bound but observationally invisible. Not because they're small, but because they're dark, because they don't reflect enough sunlight to be detected by our telescopes. These could be natural objects, remnants of Planet 9's accretion disk if it was captured. Or they could be something else, something we don't want to think about, something that makes us ask questions we're not ready to answer. Let me be clear. I'm not suggesting that there's an alien probe hiding in Planet 9's orbit. I'm not claiming that 3i Atlas is a reconnaissance shard or a fragment from a hidden base. But I am saying that the math of orbital stability is real. The Trojan regions around Planet 9, if it exists, are stable. They could shelter material for billions of years, and if that material includes objects with low albedos, if they're made of dark rock or covered in organic compounds or engineered to be non-reflective, then we wouldn't see them. They'd be invisible, even if they were there. And that raises a philosophical question. If there are regions in our own solar system that are permanently hidden from us, regions where objects could exist undetected for eons, then what might be in those regions? What might have been there since the solar system's formation? What might have arrived later? The implications are staggering. If Planet 9 has a stable population of co-orbitals, then 3i Atlas could be a fragment from that population, perturbed by a gravitational interaction or a collision sent inward toward the sun. Its unusual chemistry, its high CO2 content, its early activity, all of that could be explained by a long residence in Planet 9's orbit, exposed to cosmic radiation, bombarded by micrometeoroids, slowly altered over billions of years. And if there are more objects in that population, if the reservoir is large, then 3i Atlas might not be alone. There could be others on their way, others we won't see until they're already here. But let's push this even further. Let's ask the question that every scientist avoids, but that everyone thinks about late at night. If Planet 9's stable zones could shelter natural objects, could they shelter artificial ones? I'm talking about probes, satellites, remnants of ancient missions, objects that were placed there deliberately, either by us in some forgotten future scenario we haven't reached yet, or by someone else, something else, a long time ago. The idea sounds absurd until you remember that we've already sent probes to the outer solar system. Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, New Horizons. These spacecraft are out there right now, drifting through the Kuiper Belt and beyond, silent, mostly inactive, but still there. If we can do it, why not someone else? Why not something from another star passing through billions of years ago, leaving behind a watcher, a probe designed to observe, to record, to wait? The watcher hypothesis is speculative, I'll grant you that. It's the kind of idea that gets dismissed in peer review, that gets relegated to science fiction. But it's not impossible. The orbital mechanics work. The stability is real. And the question of whether we're alone in the universe is not going to be answered by ignoring the places we can't see. If Planet 9 is a base, if it's a gravitational anchor for a hidden population of objects, then 3i Atlas might be an emissary. It might be a signal. It might be a test. And we could be just one comet away from unmasking it. Part 11. Gravitational waves from white dwarf mergers. In 2025, astronomers announced the detection of low-frequency gravitational waves from a white dwarf binary merger. This might not sound directly related to Planet 9 or 3i Atlas, but stay with me, because the connection is profound. Gravitational waves are ripples in space-time produced by accelerating masses, and for decades we've been detecting them from violent events like black hole collisions and neutron star mergers. But white dwarf mergers are different. They're gentler, slower, producing waves at lower frequencies, detectable only by space-based observatories like LISA, the Laser Interferometer Space Antenna, which is still under development. The fact that we're now starting to detect these signals means that gravitational wave astronomy is maturing. We're not just listening for the loudest, most catastrophic events anymore. We're starting to hear the quiet ones, the subtle ones, the ones that tell us about the structure and mass distribution of the galaxy itself. And here's where it ties in. Gravitational waves are sensitive to mass. Any massive object, whether it's a star or a planet or a black hole, contributes to the local gravitational field, and that field affects the propagation of gravitational waves. If Planet 9 exists, if it's a 6 Earth mass object on a distant orbit, then it contributes to the gravitational environment of the solar system. And in principle, that contribution could be detectable. Not directly, not in the sense that Planet 9 is producing gravitational waves, but indirectly, as a modulation of the signals we're detecting from other sources. If we can measure the gravitational wave background with enough precision, if we can map out the local mass distribution, then we might be able to infer the presence of Planet 9 without ever seeing it. This is speculative, of course. Current gravitational wave detectors aren't sensitive enough to pick up the influence of a planet mass object in the outer solar system, but future detectors might be. LISA, when it launches, will be able to detect low-frequency waves from binary white dwarfs, supermassive black holes, and maybe even exotic sources we haven't thought of yet. And as the sensitivity improves, as we learn to filter out noise and isolate signals, the possibility of detecting Planet 9's gravitational signature becomes more real. It's not a guaranteed method, and it's not something that will happen soon, but it's a possibility. And in a field where we're grasping for any clue, any hint, any whisper of evidence, possibilities matter. And then there's the primordial black hole hypothesis. If Planet 9 is a PBH, if it's a 5 Earth mass black hole lurking in the outer solar system, then it would produce a different gravitational signature than a planet. Black holes warp spacetime more severely than planets of the same mass. They create stronger gravitational fields near their event horizons. They might capture dark matter particles, which would annihilate near the horizon and produce gamma rays, and they might interact with the gravitational wave background in detectable ways. If LISA or a similar detector picks up an anomaly, a deviation from the expected signal that correlates with the predicted location of Planet 9, it could be the smoking gun. It could be the evidence that finally confirms whether we're dealing with a planet or a black hole. The point is that gravitational wave astronomy is opening a new window into the cosmos. We're no longer limited to observing light, to waiting for photons to reach our telescopes. We're listening to the universe, hearing the vibrations of space-time itself, and those vibrations carry information that light cannot. If Planet 9 is out there, if it's massive enough, if it's active enough, then maybe, just maybe, we'll hear it before we see it. Maybe 3i Atlas is a messenger from a planet we'll first detect not with our eyes, but with our ears. We're no longer just watching the sky, we're hearing its secrets. Part 12. the 2025 AI Accelerated Sky Survey Breakthrough. 2025 marked a turning point in observational astronomy, and it wasn't because of a new telescope or a new instrument. It was because of software, artificial intelligence, machine learning, neural networks trained on millions of images, learning to recognize patterns, to identify anomalies, to flag transient events in real time. Sky surveys like the Zwicky Transient Facility, the Vera Rubin Observatory's Legacy Survey of Space and Time, and ATLAS have been generating petabytes of data every night, far more than human astronomers could ever analyse manually. For years, the bottleneck wasn't collecting data, it was processing it. But AI changed that. And in 2025, the systems finally matured to the point where they could identify faint moving objects, comets, asteroids, TNOs, 10 to 20 times faster than traditional methods. This is a game changer for objects like 3i Atlas. Comets are transient. They appear, brighten, fade, and disappear. If you're not looking at the right patch of sky at the right time, you miss them. But AI doesn't blink. It doesn't get tired. It doesn't need coffee or sleep or vacation. It watches continuously, scanning every frame, comparing images from different nights, tracking motion vectors, calculating orbits on the fly. And it's fast. Incredibly fast. What used to take weeks of human review now takes hours or even minutes. And that speed translates into earlier detection, more complete sky coverage, and the ability to catch objects that would have otherwise slipped through the cracks. If the simulations are correct, if Planet 9 is generating a river of debris flowing inward from the outer solar system, then AI is our best tool for detecting that river. Because the objects in that river aren't necessarily bright. They might be faint, icy fragments, only a few kilometres across, reflecting barely any sunlight. They might be on inclined orbits, passing through regions of the sky that aren't surveyed as often. They might be moving fast, appearing only briefly, before they fade back into obscurity. Human observers would struggle to find them, but AI can. And as the systems improve, as the algorithms get better at distinguishing real objects from noise, the detection rate is going to increase. We're going to find more comets, more TNOs, more inbound visitors, and some of them, maybe many of them, are going to have trajectories that point back toward the Planet 9 corridor. But there's a deeper implication here. AI isn't just finding objects faster, it's changing the way we do science. Traditionally, astronomy has been a human-driven field. Astronomers point telescopes, analyse data, write papers, propose hypotheses. But AI is starting to take on some of those roles. It's not just processing data, it's prioritising targets, suggesting follow-up observations, even identifying correlations that humans might miss. In the age of machine eyes, the discovery process is becoming automated, accelerated, almost alive. And that raises questions. Are we giving up control? Are we becoming observers of our own instruments, watching as machines make discoveries on our behalf? Or are we gaining a partner, a synthetic collaborator that can see patterns we can't, that can work tirelessly, that can help us answer questions we've been asking for decades? The answer is probably both. AI is a tool, but it's a powerful one, and like any tool, it changes the way we think and work. And in the context of Planet 9 and 3i Atlas, AI might be the key to confirming the debris injection hypothesis. If more objects start appearing from the same direction, if the flux increases, if we start seeing a pattern that matches the simulations, then AI will be the first to notice. It will flag the correlation, calculate the odds, and alert us to the possibility that we're witnessing an active planetary system at work. And that will be the moment when Planet 9 stops being a hypothesis and starts being a reality. In the age of machine eyes, the sky's secrets won't stay hidden long, especially not the ones from beyond Neptune. Part 13. The New Exoplanet Atmosphere Measurements. In 2025, the James Webb Space Telescope achieved something remarkable. It measured the atmospheric composition of an exoplanet orbiting a star 30 light-years away with unprecedented precision. Water vapour, carbon dioxide, methane, even complex organics like ammonia and hydrogen cyanide. The spectrum was detailed, clear, almost diagnostic. And it raised a question. If we can analyse the atmosphere of a planet 30 light-years away, why can't we do the same for objects in our own solar system? The answer is that we can, and we already are. 3i Atlas, with its CO2-rich coma, is a perfect target for spectroscopy. JWST has already observed it once, and future observations could reveal even more about its chemical composition. Let me tell you why this is such a profound moment in the history of astronomy. For centuries we've been limited in what we could learn about distant objects. We could measure their positions, track their motions, calculate their orbits. But their composition, their chemistry, their internal structure, all of that was locked away, inaccessible. Then came spectroscopy, the technique of splitting light into its component wavelengths and analysing the patterns, and suddenly the universe opened up. We could look at a star and know not just how bright it was, but what it was made of, how hot it was, how fast it was spinning. We could look at a galaxy and see the chemical fingerprints of generations of stars, the history of stellar birth and death written in spectral lines. And now, with instruments like JWST, we can look at planets around other stars worlds will never visit and read their atmospheric composition like a book. The exoplanet that JWST observed in 2025 was a hot Jupiter, a gas giant orbiting close to its parent star. Not a place you'd want to visit. Surface temperatures hot enough to vaporize metal, winds screaming at thousands of kilometers per hour, clouds made of silicates and exotic compounds that would be solid minerals on Earth but exist as gases in that hellish environment. And yet, from 30 light-years away, from a distance of 300 trillion kilometers, JWST could tell us what that atmosphere was made of. It detected water vapor, which was expected. It detected carbon dioxide and methane, which were predicted by models. But it also detected ammonia and hydrogen cyanide, complex molecules that tell us about the planet's formation history, about the chemical processes happening in its atmosphere, about the interplay between temperature, pressure, and photochemistry. The precision was staggering. Not just, yes, there's water vapor, but here's the abundance, here's the vertical distribution, here's how it varies with altitude and latitude. Not just, we see methane, but here's the isotopic ratio, here's the mixing ratio with other gases, here's the evidence for active chemistry driven by stellar radiation. This is the level of detail we can now achieve for worlds that are incomprehensibly far away, and it makes you wonder, if we can do that for an exoplanet 30 light-years distant, what can we do for objects in our own solar system? Objects we can point our telescopes at for hours or days without them moving out of the field of view. Spectroscopy is a cosmic lie detector. It tells us what something is made of, how it formed, where it came from. Every molecule has a unique fingerprint, a pattern of absorption and emission lines that appear when light passes through it. When photons of specific wavelengths hit a molecule, they can be absorbed, exciting the molecule to a higher energy state. Later, when the molecule relaxes, it re-emits photons, sometimes at the same wavelength, sometimes at different ones. The pattern of which wavelengths are absorbed and which are emitted is unique to each type of molecule. Water has its pattern, carbon dioxide has its pattern, methane, ammonia, hydrogen, cyanide, all of them have distinctive spectral signatures that we can identify and measure. By analysing those lines, we can identify the elements and compounds present in a comet's coma, in a planet's atmosphere, in a distant nebula. We can measure abundances, ratios, relative concentrations. We can detect trace species that make up only parts per million or parts per billion of the total. We can even measure isotopic ratios, the relative abundances of different isotopes of the same element, which tell us about nucleosynthetic processes, about the temperature and density conditions during formation, about whether material has been processed through stars or remains pristine from the primordial solar nebula. Spectroscopy is not just observation, it's interrogation. It's forcing nature to reveal its secrets through the language of light. And for 3i Atlas, spectroscopy could be the key to understanding its origin. If it's an interstellar visitor, its chemistry should reflect the conditions of another star's planetary system. Different stars have different compositions depending on when and where they formed in the galaxy. Older stars formed early in the galaxy's history have lower abundances of heavy elements, because there had been fewer generations of supernovae to produce and disperse those elements. Younger stars have higher metallicities, more carbon, nitrogen, oxygen, silicon. If 3i Atlas formed around another star, its isotopic ratio should reflect that star's composition. The deuterium to hydrogen ratio, the carbon-12 to carbon-13 ratio, the oxygen-16 to oxygen-18 ratio. All of these could be measurably different from solar system values. If it's from the Oort cloud, it should match the composition of other long-period comets. The Oort cloud is a relic of the solar system's formation, a vast reservoir of icy bodies that were scattered outward by the giant planets during the era of planetary migration. Objects in the Oort cloud should have compositions that reflect the primordial solar nebula, with some modifications from 4.5 billion years of cosmic ray bombardment and occasional heating events. We've studied many long-period comets over the decades. We know their typical composition, their ice-to-dust ratios, their volatile abundances. If 3I Atlas matches that profile, if its chemistry is consistent with being a solar system native, then the interstellar hypothesis becomes much harder to sustain. And if it's from Planet 9's debris field, it might show signatures of prolonged exposure to cosmic radiation, or exotic ices that don't match typical solar system material. Objects that spend billions of years in the outer solar system far from the Sun, in regions where temperatures are only a few dozen Kelvin above absolute zero, undergo chemical evolution driven by cosmic rays. High-energy particles from galactic supernovae and other sources constantly bombard these objects, breaking chemical bonds, creating free radicals, driving reactions that wouldn't happen at such low temperatures otherwise. Over time, this radiolysis can create complex organic molecules, can alter isotopic ratios through spallation reactions, can produce chemical signatures that are distinctive and recognizable. The CO2 to water ratio in 3I Atlas is already unusual. Most comets have a ratio closer to 1 to 10 or 1 to 20, with water dominating. Water ice is the most abundant volatile in the solar system. It makes up the bulk of cometary nuclei. Carbon dioxide is present, but typically as a minor component. When comets approach the Sun and warm up, water sublimation drives most of the activity. You see a bright coma dominated by water vapour and its dissociation products, OH radicals and hydrogen atoms. Carbon dioxide contributes, but it's secondary. But 3I Atlas is different. Its CO2 to water ratio is among the highest ever measured in a comet. That's weird. It suggests something about its formation or its history is atypical. But 3I Atlas's ratio is much higher, suggesting that it formed in a very cold environment where water was preferentially locked into the nucleus while CO2 remained volatile. There's a temperature threshold below, which water ice sublimates so slowly that it's effectively inactive, but carbon dioxide can still outgas. That threshold is around 100 to 120 Kelvin. In the outer Oort cloud, at distances of tens of thousands of astronomical units, temperatures are low enough that even carbon dioxide sublimation is minimal. But if you're slightly closer, if you're in a region where temperatures are in that critical range where CO2 is active but water isn't, you'd build up a surface enriched in carbon dioxide ice. Over time, that surface layer could become thick, shielding the water ice beneath, creating an object that outgasses mostly CO2 when it eventually gets perturbed inward. That's consistent with formation in the outer Oort cloud, or in a distant reservoir like the one predicted around Planet 9. If Planet 9 exists, if it has a debris field of co-orbital or nearby objects, those objects would be at temperatures and distances similar to the outer Oort cloud. They'd undergo similar processing, they'd develop similar surface chemistry, and if 3I Atlas came from that population, its CO2-rich composition makes sense. It spent billions of years in the cold accumulating CO2-rich layers, and now that it's been perturbed inward, now that it's warming up, that's what we're seeing sublimate first. The water ice is still there, locked in the interior, but it's the carbon dioxide that's driving the current activity. But it's not conclusive. To really pin down the origin, we need more data. We need to measure other trace species, carbon, monoxide, methane, nitrogen, organics. Each of those compounds tells a story. Each of them is a clue. Carbon monoxide is even more volatile than carbon dioxide. It sublimates at temperatures below 60 Kelvin. If 3I Atlas shows strong carbon monoxide emission, that would tell us it's been at extremely low temperatures for most of its history. Methane is interesting because it can be produced both primordially and through radiolysis of other organic compounds. Measuring the methane abundance and its isotopic composition could distinguish between these origins. Nitrogen, typically present as molecular nitrogen or as ammonia, tells us about the chemistry of the formation region. Ammonia is more easily destroyed by radiation, so its presence or absence tells us about the radiation environment the object has experienced. And then there are the organics, complex hydrocarbons, nitriles, alcohols, aldehydes, the zoo of molecules that form when simple ices are irradiated by cosmic rays or ultraviolet light. These molecules are diagnostically powerful. Different formation conditions produce different organic inventories. If 3i Atlas shows organic signatures consistent with prolonged cold storage and radiation processing, that supports the outer reservoir hypothesis. If it shows organics more typical of the inner solar system, that would be puzzling and would require explanation. If it shows organics we've never seen before, organics that don't match any known solar system formation scenario, then we have a genuine mystery on our hands, and here's where things get speculative but intriguing. If 3i Atlas is from Planet 9's orbit, if it spent billions of years in the shadow of a captured rogue planet, then its chemistry might be fundamentally different from anything else in the solar system. If Planet 9 was captured from another star, its debris field might contain material that accreted from that other star's protoplanetary disk, material with a different isotopic composition, a different chemical history. We'd be looking at solar system material mixed with extrasolar material, a hybrid object that carries signatures from two different stellar environments. That would be unprecedented. That would be a discovery that rewrites our understanding of how planetary systems interact, how material is exchanged during stellar encounters, how the early solar system might have been contaminated or enriched by foreign bodies. It might contain isotopic ratios that don't match solar abundances. The Sun has a well-characterized composition, and we assume that most material in the solar system started with similar ratios. But if 3i Atlas shows, for example, a higher deuterium to hydrogen ratio than expected, or an unusual oxygen isotope distribution, that would be a red flag. It would suggest formation around a different star, or processing in an environment very different from the solar nebula. It might have organic compounds that formed under different radiation conditions. Different stellar environments produce different radiation fields. A young, hot star produces more ultraviolet radiation. An old, cool star produces less. The balance between UV and cosmic rays affects which organic molecules form and which are destroyed. If 3i Atlas's organic inventory is anomalous, if it doesn't match models of solar system chemistry, that's another clue pointing toward an exotic origin. It might even, and this is the wildest speculation, contain molecules that suggest processing by something other than natural forces. I'm not saying it's artificial. I'm saying that if we find chemical signatures that don't fit natural models, that don't match expected formation scenarios, then we'll have to ask difficult questions. What if we detect molecules that are thermodynamically unstable, that shouldn't persist over billions of years, but are somehow present? What if we detect isotopic fractionations that require active processes, not just passive aging? What if we detect patterns in the chemical distribution that suggest organization, structure, purpose? These are unlikely scenarios. Nature is creative and produces astonishing complexity through purely physical and chemical processes. But science requires us to follow the evidence wherever it leads, and spectroscopy is how we'll get those answers. The exoplanet connection is important because it shows us what's possible. If JWST can measure the atmosphere of a planet 30 light-years away, then it can certainly measure the coma of a comet in our own solar system. The sensitivity is there. The spectral resolution is there. The wavelength coverage is there. JWST operates primarily in the infrared, which is perfect for detecting the thermal emission and absorption features of molecules like water, carbon dioxide, methane, and organics. The challenge is that comets are faint, transient, and their comas are diffuse, spread out over large areas. But JWST has dealt with diffuse targets before: nebulae, protoplanetary disks, the outskirts of galaxies. The techniques exist. The integration times might be longer, the signal-to-noise ratios might be lower, but it's absolutely feasible. But the technology is there, the sensitivity is there, and as 3i Atlas continues its journey, as it reaches perihelion and its activity increases, we'll have more opportunities to observe it, more chances to collect spectra, to analyse the data, to compare it with models and predictions. Each observation adds data points, refines our understanding, constrains the possibilities. We're not looking for a single smoking gun. We're building a case, accumulating evidence, triangulating toward the truth. And when we do, we might finally answer the question of where it came from. Was it flung from another star's planetary system? Was it ejected from the Oort cloud? Or was it thrown at us by Planet 9? If 3i Atlas carries the chemical memory of another world, what story does it tell? And whose world was it? Part 14. Ultra-high energy cosmic ray events. This year. In 2025, ground-based cosmic ray observatories reported a series of unusually energetic events. Ultra-high energy cosmic rays, charged particles moving at near light speed, striking Earth's atmosphere and triggering cascades of secondary particles. Cosmic rays are nothing new. They're constantly bombarding our planet, mostly protons and atomic nuclei accelerated by supernova, black holes, or other violent astrophysical processes. But the events in 2025 were different. They were more energetic than expected, and they seemed to show a directional bias, clustering in certain regions of the sky. Most scientists dismissed it as statistical noise, natural variation in a chaotic process. But a few researchers started asking questions. What if the cosmic rays were connected to something closer to home? What if they were being influenced by mass distributions in the outer solar system? Let me give you some context about what cosmic rays actually are, because understanding them is crucial to grasping why these 2025 detections are so strange. Cosmic rays aren't rays at all. They're particles, mostly hydrogen nuclei, protons stripped of their electrons, travelling through space at velocities approaching the speed of light. When they hit Earth's atmosphere, they collide with nitrogen and oxygen molecules, shattering them, creating showers of secondary particles that cascade downward like a cosmic avalanche. These air showers can contain billions of particles spreading over square kilometres of ground, and we detect them using arrays of sensors, scintillators, water tanks, fluorescence detectors, all working together to reconstruct the energy and trajectory of the original cosmic ray. The energy spectrum of cosmic rays is extraordinary. Most are relatively low energy, if you can call millions of electron volts low energy. But some are monsters, carrying energies equivalent to a baseball thrown at 60 miles per hour, all concentrated in a single subatomic particle. These ultra-high energy cosmic rays, the ones detected in 2025, are rare. We might see one per square kilometre per century. Their origin is one of the biggest mysteries in astrophysics. Supernovae can't accelerate particles to those energies. Even the most powerful stellar explosions fall short. You need something more extreme. Active galactic nuclei, supermassive black holes consuming matter and spitting out jets of plasma. Gamma-ray bursts, the most violent explosions in the universe. Maybe even exotic processes we don't understand yet, involving dark matter, cosmic strings, or remnants from the Big Bang itself. So when observatories in 2025 started detecting ultra-high energy events that were not only more numerous than expected, but also showed directional clustering, people paid attention. The clustering wasn't dramatic, it wasn't like all the cosmic rays were coming from one spot in the sky, but there was a statistical excess, a subtle preference for certain ecliptic longitudes, certain declinations, and when you're dealing with events that should be completely random, that should arrive geotropically from all directions, even a small deviation is significant. It means something is affecting their propagation, something is bending their paths, focusing them, or perhaps generating them through mechanisms we haven't accounted for. This is speculative, deeply speculative, but hear me out. Cosmic rays are charged particles, which means they're affected by magnetic fields. The Sun has a magnetic field, and so does the solar wind, the stream of charged particles flowing outward from the Sun. That magnetic field deflects cosmic rays, bending their paths, scattering them. This is why cosmic ray flux varies with the solar cycle. During solar maximum, when the Sun's magnetic field is strongest and most complex, cosmic ray flux at Earth decreases. The enhanced magnetic field acts as a shield, deflecting more cosmic rays away. During solar minimum, the flux increases. This is well understood, well documented, part of the background knowledge that every cosmic ray physicist carries with them. But if there's a massive object in the outer solar system like Planet 9, it could create local perturbations in the solar wind, regions where the magnetic field is compressed or twisted. Now, Planet 9 itself doesn't have a magnetic field, or at least we don't think it does. But its gravity affects the solar wind. As the solar wind flows outward from the Sun, it carries magnetic field lines with it, dragging them along like strings attached to a rotating fan. If Planet 9 is out there, its gravitational influence would create density variations in the solar wind, regions where the plasma is compressed or rarefied, and those density variations would correspond to variations in the magnetic field strength. Compressed regions would have stronger fields, rarefied regions would have weaker fields, and those variations could affect cosmic ray propagation, and those perturbations could, in principle, affect the propagation of cosmic rays. Not dramatically, not enough to create entirely new particles, but enough to modulate the flux, to create directional anomalies, to produce patterns that wouldn't exist otherwise. Think of it like this. Imagine cosmic rays as rain falling from the sky. Normally the rain falls evenly everywhere. But if you place a giant invisible object in the atmosphere, one with mass and gravity, it would create air currents around it. Those air currents would redistribute the rain, creating regions where more rain falls and regions where less falls. The total amount of rain doesn't change, but the distribution does. Planet 9 could be doing the same thing with cosmic rays, not through air currents, but through magnetic field perturbations carried by the solar wind. Now let's tie this to debris injection. If Planet 9 is actively perturbing a reservoir of icy bodies, if it's generating a stream of material flowing inward, then that stream isn't just solid objects, it's also gas and dust, released by sublimation, collisions, fragmentation. Every time two chunks of ice collide in the outer solar system, they produce debris. Every time a distant comet gets warmed slightly by cosmic rays or passing stellar radiation, it outgasses, releasing molecules into space. And all of that material, gas and dust, doesn't just disappear, it becomes part of the interplanetary medium. It drifts, spreads, interacts with the solar wind, and if there's a continuous stream of debris being injected inward from the Planet 9 region, then there's a continuous source of material being added to the interplanetary medium in specific locations, and that gas and dust could interact with the solar wind, creating additional magnetic perturbations, amplifying the effect on cosmic rays. Dust particles in space become electrically charged through photoionization and interactions with the solar wind. Once charged, they respond to magnetic fields. They can accumulate in certain regions, creating dust clouds or streams, and those dust streams would have their own magnetic signatures, their own effects on cosmic ray propagation. If the simulations are correct, if there are periodic bursts of debris injection from Planet 9, then we might expect to see corresponding structures in the interplanetary medium. Streams of dust and gas flowing inward along specific trajectories, creating magnetic anomalies that cosmic rays would have to navigate. If the simulations are correct, if there are periodic bursts of debris injection, then we might expect to see corresponding bursts in cosmic ray flux, spikes in the data that correlate with predicted injection cycles. This would be extraordinary. It would mean that Planet 9's influence isn't just gravitational, isn't just limited to perturbing orbits. It would mean that Planet 9 is affecting the entire electromagnetic environment of the outer solar system, creating signatures that we could potentially detect here on Earth, billions of kilometers away, and those signatures would be temporal, not constant. They would come and go with the debris injection cycles, with the orbital phases of Planet 9, with the geometry of the system. We might see cosmic ray anomalies appear for a few months or years, then fade, then reappear later when the conditions align again. No one has looked for this yet. No one has tried to correlate cosmic ray detections with Planet 9 simulations. The fields are too separate, the research is too specialized. Cosmic ray physicists are focused on extragalactic sources, on understanding particle acceleration in the most extreme environments in the universe. Planetary dynamicists are focused on orbits, on gravitational interactions, on the long-term evolution of the solar system. Nobody is bridging the gap, connecting the dots, asking whether these two phenomena might be related. But if they did, if someone took the cosmic ray data from 2025 and compared it with simulated debris injection timelines from Planet 9 models, if they looked for correlations, for patterns, for temporal coincidences, they might find something. They might find that the cosmic ray anomalies align with predicted high-flux periods. They might find that the directional bias points toward regions where debris streams should be most dense. But if they did, if they found a signal, it would be indirect evidence that the debris injection is real, that the river of material flowing inward is not just a theoretical prediction, but an observable phenomenon. It would mean that Planet 9's influence is measurable, detectable, confirmable through multiple independent methods. not just through TNO orbital clustering, not just through simulations, but through electromagnetic signatures, through the scattering of cosmic rays, through the modification of the interplanetary medium. It would be a convergence of evidence, multiple lines of inquiry all pointing toward the same conclusion, that there's something massive out there, something active, something that's been reshaping the outer solar system for billions of years and leaving fingerprints everywhere we look, if only we know how to read them. The challenge, of course, is disentangling local effects from galactic and extragalactic sources. Cosmic rays come from all over the universe, supernovae in the Milky Way, active galactic nuclei billions of light-years away, even remnants of the Big Bang. The cosmic ray background is noisy, chaotic, filled with variations from 1,000 different sources. Solar activity modulates it. The Earth's magnetic field modulates it. The galactic magnetic field, vast and complex, guides cosmic rays along its field lines, creating large-scale anisotropies that have nothing to do with our solar system. Picking out a tiny modulation caused by Planet 9 would be like trying to hear a whisper in a thunderstorm. You'd need exceptional signal processing, exceptional statistical rigour, and exceptional luck to isolate such a small effect from such overwhelming background noise. But it's not impossible. If the signal is there, if the pattern is real, then advanced data analysis techniques, machine learning, statistical modelling, these could tease it out. Machine learning algorithms are particularly good at finding subtle patterns in noisy data, patterns that human analysts might miss. You could train a neural network on cosmic ray arrival times, energies, and directions, feed it the Planet 9 simulation outputs, and ask it to look for correlations. You could use Bayesian statistical methods to calculate the probability that an observed cosmic ray clustering is consistent with debris injection, models versus pure chance. You could combine data from multiple observatories, increasing your statistical power, reducing your uncertainties. The tools exist. The data exists. What's missing is someone willing to do the work, to take the risk of pursuing an idea that most scientists would consider fringe, speculative, unlikely. And if they do, we'll have a completely new way of probing the outer solar system. Not with light, not with gravitational waves, but with cosmic rays. We'd be using the universe's own particle accelerators, the most energetic phenomena in existence, as probes to map the structure of our cosmic neighbourhood. We'd be turning cosmic rays from a mystery into a tool, from a phenomenon we study into a technique we use. And that would open doors to understanding not just Planet 9, but the entire architecture of the outer solar system. The distribution of mass, the structure of the interplanetary medium, the dynamics of debris streams, all of it could become visible through the lens of cosmic ray modulation. Maybe, in the whispers of cosmic rays, we hear the echoes of a hidden giant. Part 15. Quantum simulation advances in 2025. In 2025, quantum computing reached a milestone that most people outside the field barely noticed. A team at a quantum research lab successfully simulated a 10-body gravitational system over a billion-year timescale using a quantum-inspired analog simulator. That might not sound impressive until you understand what it means. Classical n-body simulations, the kind used to model Planet 9 and the outer solar system, are computationally expensive. Simulating even 100 objects over a few million years requires massive supercomputers and weeks of processing time, and the longer the timescale, the more uncertainty accumulates. Small numerical errors compound, orbits drift, predictions become unreliable. Quantum simulators, if they work, could change that. They could run the same simulations orders of magnitude faster, with less error, over much longer timescales. And that could be the key to finally pinning down Planet 9's parameters. Here's why this matters. The biggest challenge in the Planet 9 hypothesis is the parameter space. We don't know the planet's exact mass, orbital elements, inclination, eccentricity. We have ranges, educated guesses based on the clustering of TNO orbits, but not precise values. And different parameter choices produce different predictions. A 5 Earth mass planet on a certain orbit produces 1 flux of inbound objects. A 7 Earth mass planet on a slightly different orbit produces another. Testing all possible combinations with classical simulations is prohibitively expensive. But with quantum simulators, we could explore the entire parameter space in a fraction of the time. We could test exotic models, binary perturbers, primordial black holes, complex resonance scenarios, all of them, and see which ones match the data, and we could do it with enough precision to make definitive predictions. And here's the kicker. Quantum simulations could also let us peer into the deep past and far future of the solar system. We could simulate what the outer solar system looked like 1 billion years ago, before the current configuration settled. We could track the evolution of the detached population, see how objects were scattered or captured, identify the moments when debris injection was strongest. And we could run the simulation forward, predicting where Planet 9 will be in 1 million years, what the flux of inbound objects will look like, whether we're currently in a high activity phase or a low one. That kind of insight would be transformative. It would turn Planet 9 from a hypothesis into a predictive model, something we could test, refine, and ultimately confirm or falsify with observational data. But there's an even deeper implication. If quantum computing allows us to simulate the outer solar system with unprecedented precision, then we'll be able to test not just whether Planet 9 exists, but what it is. We could run simulations with a super-Earth and compare them to simulations with a primordial black hole. We could model captured planets, ejected planets, binary systems, all of them, and see which scenario best reproduces the observed distribution of TNOs, the flux of inbound objects like 3I Atlas, and the stability of the Kuiper Belt. The quantum computer wouldn't just tell us where Planet 9 is, it would tell us what Planet 9 is made of, where it came from, and what it's been doing for the last 4.5 billion years. The technology isn't there yet. Current quantum simulators are still experimental, limited to small systems and short timescales. But the progress is accelerating. In 5 years, 10 years, we might have quantum computers capable of running full solar system simulations with hundreds or thousands of bodies over billions of years. And when that happens, the mystery of Planet 9 will move from the realm of speculation into the realm of computation. We'll be able to simulate every scenario, test every hypothesis, and finally determine which one is correct. We're developing the technology not just to see hidden planets, but to simulate their shadows with quantum precision. And that brings us back to 3I Atlas. If quantum simulations confirm that Planet 9 is actively generating a river of debris, if they predict a flux of inbound objects with specific velocity distributions, specific chemical signatures, specific arrival rates, then we'll know what to look for, we'll know where to point our telescopes, we'll know how to distinguish Planet 9 debris from genuine interstellar visitors, and we'll know whether 3I Atlas was a random visitor, a cosmic accident, or something more deliberate. If our biggest mysteries lie at the edges of the solar system, quantum computing may be the key to finally illuminating them, and perhaps proving whether 3I Atlas was a random visitor or a warning shot. So where does this leave us? We started with a comet, 3I Atlas, supposedly interstellar, supposedly from another star. But the deeper we looked, the stranger it became. Its trajectory points back toward the Planet 9 zone. Its chemistry doesn't quite match typical interstellar objects. Its activity pattern is anomalous. And the simulations, the clustering data, the 5 sigma statistical confidence, all of it suggests that Planet 9 is real, that it's active, that it's generating a stream of debris flowing inward from the outer solar system. 3I Atlas might not be from another star. It might be from our own solar system's hidden reaches, flung inward by a ghost planet we've never seen. But even if that's true, even if 3I Atlas is solar in origin, the questions don't stop. They multiply. If Planet 9 is real, where did it come from? Is it native, ejected from the inner system billions of years ago? Or is it captured, a rogue world stolen from another star during the sun's infancy? And if it's captured, what else did it bring with it? What debris? What moons? What secrets might be hiding in its stable zones, orbiting in the darkness, waiting to be discovered? And if Planet 9 isn't a planet at all, if it's a primordial black hole, a remnant from the Big Bang, then what does that tell us about the universe, about dark matter, about the forces that shaped our cosmic neighbourhood? Every answer generates new questions. Every piece of evidence points towards something larger, something more complex, something that challenges our understanding of the solar system's architecture. We thought we knew our cosmic home. We thought we had mapped it, catalogued it, understood its boundaries. But we were wrong. There's a ghost out there, a hidden force, a planet or a black hole or something else entirely, and it's been silently sculpting the outer solar system for billions of years. It's been watching, it's been waiting, and now it might be sending us messages. 3i Atlas is one message, but it won't be the last. If the simulations are correct, if the river of debris is real, then more objects are coming. More comets, more asteroids, more icy fragments hurtling inward at hyperbolic velocities, each one carrying a piece of the puzzle, each one a clue to the nature of the hidden giant. And with AI watching the skies, with quantum computers running simulations, with gravitational wave detectors listening to space-time itself, we're finally developing the tools to solve this mystery. The ghost won't stay hidden forever. We're getting closer. And when we finally find it, when we finally see Planet 9 or detect its black hole shadow or confirm its gravitational signature, the implications will be profound. We'll have discovered a new planet in our own solar system, the first in nearly 2 centuries. Or we'll have discovered something even stranger, a primordial black hole, a captured alien world, a binary system, a hidden architecture that reshapes everything we thought we knew. But until that moment comes, we're left with fragments, with anomalies, with objects like 3i Atlas that don't quite fit the story we've been telling ourselves. And maybe that's the point. Maybe the universe is trying to tell us something. Maybe it's reminding us that we don't have all the answers, that there are still mysteries lurking in the darkness, that the solar system is larger and stranger and more dangerous than we ever imagined. We've always believed that the outer solar system was a graveyard, a frozen archive, a place where nothing happens. But what if we were wrong? What if it's a battlefield? What if Planet 9 isn't just a passive observer, but an active participant, a force of chaos, a planet that throws rocks? And if that's true, if Planet 9 is out there right now, perturbing debris, generating flux, sending objects like 3i Atlas our way, then we need to ask ourselves a very uncomfortable question. Are we safe? Is Earth safe? The objects we're detecting are small, a few kilometres across, nothing that could threaten our planet directly. But the simulations predict a continuous stream, a river of debris flowing inward, and rivers can flood, rivers can surge. If Planet 9 enters a high activity phase, if the alignment shifts, if the resonances change, we could see a dramatic increase in the flux of inbound objects. More comets, more impacts on the inner planets, more opportunities for catastrophic collisions. Planetary defense has always focused on near-Earth asteroids, on the rocks we can see coming. But nobody has been thinking about the rocks thrown by a hidden planet from the outer darkness. Nobody has been preparing for that scenario. Maybe 3i Atlas is a warning. Maybe it's the first shot in a barrage we don't yet see coming. Or maybe it's just a comet, a chunk of ice and rock following the laws of gravity, indifferent to our fears and our questions. We don't know yet. We won't know until we find Planet 9, until we map its orbit, until we understand its influence. But one thing is certain, the outer solar system is not empty. It's not quiet. It's alive with forces we're only beginning to comprehend. And somewhere out there, in the darkness beyond Neptune, beyond the Kuiper Belt, beyond the edge of everything we can see, there's a ghost, a massive, hidden giant, sculpting the cosmos, throwing fragments into the void, and waiting. Always waiting. The question isn't whether Planet 9 exists anymore. The 5 Sigma confidence tells us it almost certainly does. The question is what it's been doing all this time, and what it's about to do next. Because if the simulations are right, if the debris injection is real, if the river is flowing, then 3i Atlas is just the beginning. More visitors are coming, more messages from the outer, dark, more pieces of the puzzle. And when we finally assemble all those pieces, when we finally see the complete picture, we might discover that our solar system is far stranger, far more active, and far more perilous than we ever dared imagine. So tonight, as you look up at the stars, remember that not all the mysteries are out there in the distant cosmos. Some of them are right here, hiding in our own backyard, lurking in the cold and the dark where no telescope can reach. And some of those mysteries, like 3i Atlas, occasionally come to visit. Occasionally come screaming inward at 150,000 miles per hour, carrying secrets from the edge of the solar system, bearing the gravitational fingerprints of a planet we've never seen. A ghost with purpose, a hidden giant, a force that might at any moment decide to throw another rock our way. And we'll be watching, waiting, wondering if the next visitor will be as small as 3i Atlas, or something much, much larger. The universe is full of ghosts, and one of them lives right next door.